Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine you are an astronaut. You have just completed the most perilous, technologically complex journey in human history.
Right. You've trained for years for this exact moment.
Exactly. You are finally stepping out of your lander and onto the surface of the moon.
Yeah.
You expect the profound, absolute silence of the vacuum of space. You expect that strange, floating sensation of the low gravity.
Which is what? Only about 1/6 of what you feel right now sitting in your chair.
Right. And you expect the breathtaking view of Earth hanging like a fragile blue marble against an endless black void.
Mm-hmm.
You've prepared for the cold. You've prepared for the isolation. But what you absolutely do not expect, what completely blindsides you, is that the greatest, most immediate threat to your survival isn't the vast vacuum of space above your head.
No, it's definitely not.
It is the dirt beneath your boots.
It's a brilliant image to start with, honestly, because it perfectly captures that fundamental disconnect between our romanticized vision of space exploration and the really gritty, highly dangerous reality of planetary surface operations.
Yeah, totally.
When we look up at the moon from Earth, we see this static, serene, silvery disk. It looks dead.
Like it's just peaceful and geologically inactive.
Right. But the moment you actually set foot on the surface, you are stepping into an environment blanketed in a material that is actively, continuously, and aggressively hostile to both human biology and mechanical engineering.
And we are talking about lunar regolith, the omnipresent layer of dust and pulverized rock that just coats the moon.
Yes.
For decades, stretching all the way back to the Apollo missions, this dust was considered the ultimate operational nightmare. It was like the monster hiding under the bed of space exploration.
Oh, absolutely.
But, and this is where it gets incredibly fascinating, we are going to explore a monumental paradigm shift currently taking place in aerospace engineering. We're looking at how this highly dangerous dust is transitioning from being our greatest enemy to the absolute foundational resource for building human infrastructure beyond Earth.
Yeah, it's a massive shift.
Okay, let's unpack this. Because it's a massive conceptual leap to go from this dust is going to kill our astronauts to we are going to build our future extraterrestrial cities out of this exact same stuff.
Well, to truly appreciate the elegance of the solution, we have to forensically examine the hazard itself first.
Right. We need to know the enemy.
Exactly. The ingenuity of modern in situ resource utilization, or ISRU, just doesn't make sense unless we deeply understand the mechanics of why lunar dust was such an existential threat to those original lunar pioneers.
So we can't just say the dust was bad.
No, we need to look at the physics of its formation. We need to look at its interaction with the Apollo hardware.
Let's crack open those Apollo mission logs then, because the astronauts weren't just complaining about, tracking a little dirt into the lunar module.
Not at all.
They described the dust as invasive on a microscopic level. It was fundamentally damaging. Like, it coated their bright white spacesuits until they were dark gray.
Which is a huge problem because then the suits absorb solar heat instead of reflecting it.
Right. And it fouled their optical instruments. But what always strikes me is the mechanical degradation.
Oh, the wear and tear was unbelievable.
These were highly engineered, incredibly expensive pieces of equipment with exacting aerospace tolerances, right?
Yeah.
And this dust was finding its way into the sealed moving parts and just grinding them into uselessness within days.
Yeah, take the Apollo 17 rover, for example.
Yeah.
Harrison Schmitt and Eugene Cernan essentially had to construct a makeshift fender out of laminated maps and duct tape.
Duct tape on the moon. I love that detail.
It's amazing. But they had to do it because the regolith kicked up by the wheels was coating the rover's radiators. Without that makeshift fix, the rover's batteries would have overheated and failed.
Which would have left them stranded miles from the lunar module.
Exactly. The dust was actively dismantling their thermal control systems. And the degradation of the spacesuit joints was severe, too.
How bad did it get?
Well, the wrist and shoulder bearings on the pressure suits were becoming stiff and incredibly difficult to operate by the end of just a 3-day surface stay.
Wow, only 3 days.
Yeah. If they had stayed for a month, the suits might have locked up entirely.
And then there is the biological threat, which is wild. When the astronauts returned to the lunar module, pressurized the cabin and finally took off their helmets, they actually smelled the dust.
Yes, the famous gunpowder smell.
Right. They universally described it as smelling like spent gunpowder.
Yeah.
And it immediately began irritating their respiratory systems.
Harrison Schmidt actually experienced what he called lunar hay fever.
Yeah, severe congestion, sneezing, watery eyes.
Right, and you have to remember, you are in an environment where a compromised respiratory system or a failed seal means instant death.
And the very ground you are walking on is actively trying to infiltrate your lungs and eat through those seals.
Exactly.
But this is where I need to push you on the physics because, the dirt in my backyard doesn't act like a biological weapon or an industrial grinding paste. What specifically makes lunar regolith so uniquely destructive compared to terrestrial soil?
The fundamental difference comes down to the complete absence of a hydrosphere or an atmosphere.
Okay, so no water, no air.
Right. Because the moon has no liquid water and no atmospheric friction, it has no weathering process. On Earth, wind and water constantly tumble and smooth out particulate matter over time.
Like river stones getting smooth.
Exactly. But lunar regolith is formed almost exclusively by hypervelocity micrometeorite impacts over billions of years.
So things are just smashing into it constantly.
Yeah. A microscopic piece of space debris slams into the lunar bedrock at 30,000 miles per hour in a complete vacuum, and it instantly shatters and vaporizes the rock.
So instead of smooth, polished particles like we have here, we are dealing with freshly fractured shards.
Exactly. When that rock vaporizes and condenses or just shatters, the resulting microscopic fragments remain exactly as they were the millisecond they were created.
They don't get worn down.
No, they are jagged, highly irregular, and incredibly abrasive. The lunar surface is essentially coated in a thick layer of microscopic, jagged glass shards.
Wow. Microscopic glass shards.
Yeah. So when a particle of regolith gets into the bearing of a spacesuit, it doesn't roll like a ball bearing. It acts like a microscopic saw blade.
That sounds awful.
It catches, it gouges, and it actively cuts into the surrounding material with every single movement the astronaut makes.
That perfectly explains the mechanical grinding and the abrasive damage. It's literally like trying to lubricate a machine with crushed diamonds.
That's a great analogy.
But that doesn't explain the aggressive adherence. The literature constantly refers to the dust as electrostatically charged and chemically reactive. Why does it cling to absolutely everything, even vertical surfaces?
This is where the lunar plasma environment becomes critical. The moon has no global magnetic field to deflect solar radiation, right? And no atmosphere to absorb it.
So the surface just gets baked.
Completely. During the 2-week-long lunar day, the surface is bombarded by unfiltered ultraviolet and X-ray radiation from the sun. This high-energy radiation triggers the photoelectric effect on the surface of the dust grains.
Okay, the photoelectric effect, meaning it's literally knocking electrons off the particles.
Precisely. It strips the electrons away, which leaves the dayside dust with a strong, positive electrostatic charge.
Okay, so the UV light blasts the electrons away, leaving positive charge. But what happens on the night side? Or like in the deep shadows of craters?
On the night side, or even in the deep shadows cast by boulders in the lunar module itself, the physics completely flip.
Wait, really? How?
Those shadowed areas are bombarded by electrons from the solar wind plasma, giving the dust in those regions a strong negative charge.
So the light side is positive and the dark side is negative.
Yes. You have this incredibly complex electrostatic environment. And when an astronaut, who is also accumulating static charge as they move, walks through these different zones...
Oh man, they essentially become a giant static magnet.
Exactly. The dust doesn't just passively settle onto them. It aggressively leaps off the surface and adheres to the fabric of the suit, the visors, the tools.
It's like static cling, but on a planetary lethal scale.
And because the vacuum prevents any moisture from dissipating that charge, it just stays there.
But wait, what about the gunpowder smell? You mentioned the dust is chemically reactive. How does a rock sitting in a vacuum for 1 billion years remain chemically reactive?
Well, it's precisely because it's in a vacuum.
Oh, interesting.
Yeah. When a micrometeorite impact fractures a silicate rock on the moon, it breaks the chemical bonds in the crystal lattice.
Okay.
On Earth, those broken bonds, which are highly reactive, would immediately react with oxygen or water vapor in the air and neutralize. They would oxidize.
Right, they'd rust or just balance out.
Exactly. But on the moon, there is no oxygen and no water. So those fractured bonds remain unsatisfied, dangling, and desperate to connect with something.
And they stay like that for millions of years.
They stay in that highly reactive state indefinitely.
Ah, I see. So when the astronauts track that dust into the lunar module and then repressurize the cabin with oxygen?
The dust immediately reacts with the oxygen and the moisture in the cabin air. The rapid oxidation of those unsatisfied bonds is what created that distinct, pungent smell of spent gunpowder.
That is wild. And when an astronaut inhaled those particles...
Right, those jagged reactive glass shards were not just physically tearing at the tissues in their lungs, they were actively reacting chemically with the moisture inside the human respiratory system.
So it's a physical and a chemical attack on the body.
Yes. The long-term toxicity of inhaling lunar regolith is a massive area of ongoing aerospace medical research.
When you lay out the physics and the chemistry like that, I mean, the jagged geometry, the photoelectric charging, the dangling chemical bonds, you really feel the profound everyday operational anxiety this must have caused.
It was constant. It wasn't just a nuisance. It was an active, multifaceted attack on the mission hardware and the astronauts themselves.
Which brings us to the great engineering crossroads. Because if we know that the lunar environment is covered in this incredibly destructive, universally hostile material, the most logical human reaction is to avoid interacting with it.
Sure, that's instinctual.
Right. If I'm tasked with building a permanent lunar base, my first instinct is to design pristine, fully enclosed modules here on Earth, like titanium structures, perfect seals.
Build a bubble of Earth.
Exactly. Build a bubble of Earth, drop it on the moon, and keep the regolith out. I know we don't do that, but I want to push on why we don't just do that. Orbital manufacturing is advancing. We have heavy lift vehicles now. Why is the bring everything with us model so fundamentally broken?
It comes down to the relentless, unforgiving tyranny of the Tsiolkovsky rocket equation and the sheer economic weight of planetary gravity wells.
Okay, explain that.
It's all about mass fraction. To understand why we can't just ship a titanium base to the moon, you have to look at the gear ratio of spaceflight. To launch a single kilogram of useful payload from Earth into low Earth orbit requires a massive amount of propellant.
Like how much?
Often 10 to 20 times the mass of the payload itself, just to overcome Earth's gravity and atmospheric drag.
Right, so the vast majority of a rocket sitting on the pad is just the fuel needed to lift the fuel.
Precisely. But low Earth orbit is only step one. If you want to take that same kilogram of payload and push it out of Earth orbit, transit to the moon, enter lunar orbit, and then perform a powered descent to land safely, the amount of propellant required grows exponentially.
So every ounce of steel, every pane of glass, every liter of water you want to land on the moon means launching hundreds of ounces of highly explosive rocket fuel from Earth.
Yes, the mass penalty is staggering. Even with the advent of reusable super heavy launch vehicles, the logistics of transporting bulk construction materials is just economically prohibitive.
So if I want to build a radiation-shielded habitat on the moon, and I need a meter-thick wall around it, shipping those concrete or steel blocks from Earth would bankrupt any space agency.
You'd be impossible. It's essentially paying an exorbitant luxury tax on heavy dirt.
Which is why the paradigm of in situ resource utilization, or ISRU, is not just a clever engineering trick.
No, it is an absolute non-negotiable requirement for establishing a permanent human presence beyond Earth. We have to live off the land. We must sever the umbilical cord of bulk material supply stretching back to Earth.
And that forces us into a very uncomfortable reality, doesn't it?
Yes. The only bulk material available to us on the lunar surface is the regolith.
And here is the massive friction point in this entire concept.
Yeah.
We just spend a considerable amount of time meticulously detailing exactly why this specific material is an absolute nightmare.
Yeah.
It's jagged, abrasive, electrostatically charged, chemically reactive. It destroys aerospace tolerances in human lungs.
Right.
And now the mandate is you have to build your highly sensitive life support infrastructure out of this exact same material.
That's the challenge.
We're essentially being forced by a cosmic budget constraint to use the monster under the bed to build the house. Are engineers just reluctantly settling for a terrible building material because they can't afford anything better?
What's fascinating here is that the narrative shifts from an engineering compromise to an engineering triumph. As material scientists have analyzed the granular mechanics and thermophysical properties of lunar regolith, they aren't just figuring out how to tolerate it.
Oh, really?
Yeah. They are discovering that the exact properties that made the dust an absolute nightmare for mechanical joints and human lungs make it an exceptionally ideal material for advanced manufacturing and solid-state construction.
Wait, the hazard itself is a secret weapon.
It really is.
Let's break that down because it sounds totally counterintuitive. How do the sharp edges and the irregular morphology make it good for building? If I have a material that grinds moving parts to dust, how do I turn it into a structural beam without it just crumbling?
The mechanism relies heavily on advanced sintering technologies.
Sintering, okay.
Sintering is the process of compacting and forming a solid mass of material by applying heat or pressure, but crucially, without melting it to the point of complete liquefaction.
So you take a powder, you heat it to a specific point below its melting threshold, and the particles fuse together at their contact points.
Exactly.
I understand the basic concept of sintering ceramics here on Earth, but how does the jagged nature of lunar dust specifically enhance this?
Think about the internal friction of the particulate mass. If you try to compress a pile of smooth, wind-weathered earth sand, like the spherical silica sand you find in a desert, the particles tend to slip and slide past one another.
Right, there's no grip.
The smooth surfaces provide very little mechanical friction. But lunar regolith is composed of those highly irregular, jagged, shattered glass shards. When you compress them, they don't slide.
Ah, they catch on each other.
Yes, the sharp edges catch, intertwine, and mechanically lock together with incredible shear strength.
So the lack of weathering is actually a massive structural advantage.
Huge advantage.
The very geometry that allows the dust to catch and grind inside a spacesuit bearing allows it to interlock and hold itself together when compressed into a brick. It's like the difference between trying to build a structure out of perfectly smooth ball bearings versus building it out of thousands of interlocking puzzle pieces.
That is exactly it. The mechanical interlocking provides the initial compaction strength. But to make it a durable, load-bearing structure, we have to induce thermal friction.
The heat part of sintering.
Right. And this brings us to the specific chemical composition and mineralogy of the regolith, which is highly responsive to directed energy.
Let's get into the chemistry of the sintering process then. What exactly is in this dust that makes it so amenable to being baked into solid rock?
Well, lunar regolith is fundamentally composed of silicates and metallic oxides, minerals like plagioclase feldspar, pyroxene, and olivine.
Okay, standard rock stuff.
But one of the most crucial components, particularly the darker mare regions of the moon, is a mineral called ilmenite, which is an iron-titanium oxide.
Iron and titanium, good building blocks.
Yes, but furthermore, because the regolith has been bombarded by the solar wind for billions of years, it is embedded with billions of microscopic nanophase iron particles.
Nanophase iron particles. Hold on, so there is literally microscopic pure iron distributed throughout the dust.
Yes. The solar wind contains hydrogen protons. When they slam into the regolith, they chemically reduce the iron oxides and the minerals, leaving behind tiny droplets of pure metallic iron inside the glass matrices of the dust grains.
That's incredible.
It is. And these nanophase iron particles are a game changer for ISRU because they give the regolith incredibly unique dielectric properties.
Dielectric properties, meaning how the material interacts with electric fields and electromagnetic radiation?
Precisely. Because of this embedded nanophase iron, lunar regolith is highly absorptive of microwave radiation.
Wait, microwaves?
Yeah. If you blast lunar dust with a targeted microwave emitter, the nanophase iron particles couple with the microwave field and heat up incredibly fast. They essentially cook the surrounding silicate glass from the inside out.
Oh, wow.
So we don't need to bring massive, heavy, conventional thermal ovens to the moon to bake these bricks. We can use relatively lightweight, solid-state magnetrons.
The exact same technology that powers the microwave oven in my kitchen.
The exact same technology, just scaled up and focused.
But let me push back on that for a second. Hauling a giant industrial microwave array to the moon still sounds like a significant mass penalty. If mass is the ultimate enemy, wouldn't it be easier to just use the massive fusion reactor that's already in the sky? The sun.
That's a logical thought.
Right. Can't we just use giant magnifying glasses or solar concentrators to melt the dust?
Solar concentrators are absolutely a viable pathway, and several architectural concepts rely on them. You use lightweight mylar mirrors to focus raw sunlight into a high-temperature beam, which can easily melt regolith.
Sounds super mass efficient.
It is highly mass efficient. However, solar concentrators have a massive operational limitation. They only work during the lunar day.
Ah, of course.
If you are operating near the equator, you have 14 days of sunlight, followed by 14 days of total darkness, during which your construction halts completely.
You'd lose half your year just waiting in the dark.
Exactly. Microwave sintering, or laser sintering powered by nuclear isotopes or stored battery banks, allows for continuous 247 manufacturing operations. regardless of solar illumination.
That makes a lot of sense.
Plus, microwaves allow for much finer volumetric heating, whereas solar concentrators really only melt the very top surface layer.
Okay, I see. The microwaves penetrate the bulk material, utilizing those nanophase iron particles to fuse the dust at depth, creating thick, solid, interlocking structures.
Got it.
So we are taking this jagged, highly abrasive, chemically reactive dust, mechanically locking its sharp edges together, and using targeted microwaves to fuse the iron and silicates into solid stone.
It's beautiful, isn't it?
It completely flips the narrative. Instead of spending billions of dollars designing specialized vacuum systems and advanced seals to fight the best, like trying to push the ocean back with a broom, we are weaponizing its specific mineralogy and morphology to build our infrastructure.
It is a perfect example of turning a constraint into an affordance. Now that we have established the thermophysical mechanics of how we bind the regolith, the critical question becomes, what are we building first?
Right. Because if you have this manufacturing capability, where do you direct it? When I think of a lunar base, my mind immediately jumps to habitats.
Most people's do.
I picture pressurized domes, airlocks, laboratories, maybe greenhouses, the places where the humans are actually going to live and breathe. But when you look at the current Artemis architecture, the first major structural elements they want to print out of regolith aren't habitats at all.
No, they're not.
They're landing pads. Why is a parking lot the absolute highest priority for lunar construction?
Because without hardened landing pads, you cannot land the massive cargo vehicles required to build the habitats in the first place without causing catastrophic damage to everything in the vicinity.
Causing damage just by landing.
Yes. To understand this, we have to look closely at the fluid dynamics and physics of a rocket exhaust plume interacting with a planetary surface in a hard vacuum. This introduces a phenomenon known in the aerospace community as the plume surface interaction, or simply the plume effect.
Okay, let's dissect the plume effect. We've seen Apollo landers touch down. They kicked up a bunch of dust, sure, but it didn't destroy the lunar module. What changes when we scale this up to modern heavy-lift lunar landers?
Well, the Apollo lunar module descent engine produced about 10,000 pounds of thrust.
Okay.
The next generation of human landing systems, like the modified Starship vehicles being developed for Artemis, will produce hundreds of thousands, if not millions of pounds of thrust.
Oh, wow. That is a vastly larger, heavier vehicle coming down.
Massive difference. Now, when a rocket engine fires in Earth's atmosphere, the ambient atmospheric pressure acts as a confining boundary. It pinches the exhaust plume into a relatively tight vertical column.
Okay, the air pushes back against the exhaust.
Right. Furthermore, if a rocket lands in a terrestrial desert, it kicks up a massive cloud of sand. But atmospheric friction, drag, rapidly decelerates those particles. And Earth's 1G gravity pulls them back to the ground quickly. The debris field is highly localized.
But on the moon, there is no ambient atmospheric pressure to pinch the plume and no air resistance to slow down the debris.
Exactly. When a rocket exhaust plume hits the lunar surface in a vacuum, the gas transitions from continuum flow to free molecular flow. Because there is zero atmospheric pressure pushing back against it, the superheated gas expands violently and radially, parallel to the ground.
It just shoots outwards.
It shears across the surface of the regolith at supersonic speeds.
And it picks up that top layer of loose, jagged dust along the way.
It doesn't just pick it up. It entrains it and accelerates it to phenomenal velocities. Because there is no air resistance to slow the dust down, and because lunar gravity is only 1/6 of Earth's, these tiny, highly abrasive particles travel at ballistic trajectories.
How fast are we talking?
They are accelerated to velocities exceeding 3,000 meters per second.
3,000 meters per second? That's faster than a high-velocity rifle bullet.
It is an omnidirectional, hypervelocity sandblaster. And because there is no atmosphere to stop it, this ejecta can travel for immense distances.
I can't even imagine the damage that would cause.
Well, we have historical evidence of it. During the Apollo 12 mission, the lunar module Intrepid landed about 160 meters away from the old robotic Surveyor 3 probe, which had been sitting there for years.
Oh, right. They visited the old probe.
Yes. The Apollo 12 astronauts walked over, removed the camera from Surveyor 3, and brought it back to Earth for analysis.
What did the analysis show?
The engineers found that the entire side of the Surveyor probe facing the Apollo 12 landing site had been extensively pitted, scoured, and sandblasted by the regolith kicked up by the descent engine.
From 160 meters away.
And that was from a relatively small lander. If you try to land a massive 100-ton cargo vehicle anywhere near an established lunar base, the plume ejecta will scour the optics of telescopes, shred the delicate photovoltaic cells of solar arrays.
Blast through thermal blankets, sandblast the life support module.
Exactly. It is an unacceptable mission risk.
Yeah.
You cannot build a base if every resupply ship effectively detonates a fragmentation grenade of abrasive dust upon arrival.
So to protect our incredibly expensive, delicate life support infrastructure from the deadly dust being weaponized by our own rockets, we have to preemptively melt that dust into a hardened parking lot.
Yes. The architecture demands that we send robotic, autonomous rovers ahead of the human missions.
Oh, before people even get there.
Exactly. These rovers will grade the surface, utilize microwave or solar sintering techniques to fuse the loose regolith into interlocking tiles or a continuous vitrified pad and create a solid landing zone.
And then the heavy lifters come in.
Right. When the heavy lift vehicle descends onto that vitrified pad, the exhaust plume hits solid rock. There's no loose regolith to entrain, no ejecta sheet, and the risk of the sandblaster effect is entirely neutralized.
It's an incredible irony. We have to use the hazard to build the shield against the hazard. The very material that threatens to sandblast our solar panels is melted down to create the safe zone.
Is deeply ironic.
And I have to assume this logic scales up beyond just landing pads. Because once you land safely and mitigate the plume effect, you still have to survive the rest of the lunar environment, which is actively trying to eliminate you in several different ways. Landing is just the prologue.
Oh, absolutely.
Let's talk about the actual habitation. Once you step off that sintered landing pad, what are the primary environmental threats that ISRU helps mitigate?
The two most immediate persistent threats to human habitation on the lunar surface, beyond the vacuum itself, obviously, are the extreme thermal environment and the lethal ionizing radiation. And both of these problems demand massive amounts of bulk material to solve.
Let's tackle the thermal environment first. When we say extreme temperature swings, what does that actually mean in numbers?
Because the moon lacks an atmosphere to distribute heat or provide an insulating blanket, the surface temperatures are dictated entirely by direct solar illumination.
So the sunlight is brutal.
Extremely. During the lunar day, with the sun directly overhead, the regolith at the equator bakes at temperatures exceeding 250 degrees Fahrenheit, or about 120 degrees Celsius.
It is significantly hotter than boiling water.
Yes, but the moment the sun drops below the horizon, and the 14-day lunar night begins, the temperature plummets instantly into the deep freeze of space, dropping down to minus 208 degrees Fahrenheit or minus 130 degrees Celsius.
That is nearly a 460-degree Fahrenheit thermal swing. If I just take a high-tech, thin-walled aluminum or composite habitat module that I manufactured in a clean room on Earth, fly it up there, and set it on the surface, the thermal expansion and contraction alone would stress the material to the breaking point.
The seams would flex, the seals would degrade, it would be a nightmare.
And the energy required to keep the interior at a comfortable 72 degrees for the astronauts would be astronomical. You'd be running massive air conditioners during the day and massive heaters at night.
Exactly. A thin metallic shell is highly conductive and offers terrible thermal inertia. This is where the regolith becomes essential.
Because it's a good insulator.
Right. Rock and pulverized soil are exceptionally poor conductors of heat, which makes them excellent thermal insulators. If you take those sintered regolith bricks, or if you use an autonomous 3D printer to extrude a thick shell of regolith directly over your pressurized aluminum habitat,
you create massive thermal mass, like burying the habitat or building a thick dirt igloo over it.
Precisely. A layer of regolith a few meters thick acts as an incredible thermal buffer. During the searing heat of the lunar day, the outer layer of the regolith absorbs the solar energy, but because of its low thermal conductivity, that heat takes a very long time to penetrate down to the habitat.
Oh, so it delays the heat wave.
Yes. By the time the heat wave reaches the inner module, the 14-day lunar night has likely begun. The regolith then acts as a blanket, slowly releasing that stored heat and insulating the habitat against the freezing vacuum of the night.
It passively smooths out the massive 460-degree thermal swing,
drastically reducing the active power load required for life support.
That's brilliant. You are using the mass of the moon itself as a passive thermostat. But what about the radiation? Because thermal insulation is one thing, but keeping the astronauts from developing acute radiation sickness is another entirely. How bad is the radiation environment on the surface?
It is severely limiting. Without a magnetosphere or an atmosphere, the lunar surface is constantly bombarded by two primary sources of ionizing radiation.
What are they?
First, you have solar proton events, basically solar flares, which are bursts of high-energy protons from the sun. These can be acutely lethal if an astronaut is caught outside without shielding.
And the second?
Second, you have galactic cosmic rays, or GCRs. These are heavy, extremely high-energy atomic nuclei traveling from deep space at nearly the speed of light.
And I imagine a thin aluminum wall does very little to stop a particle traveling at the speed of light.
It's actually worse than doing nothing.
Wait, worse? How?
When a high-energy galactic cosmic ray strikes a thin, dense metal shield like aluminum, it shatters the atomic nuclei in the metal, creating a cascade of secondary radiation, including neutrons and X-rays.
Oh, no.
This is known as Bremsstrahlung, or breaking radiation. Sometimes, sitting behind a thin shield of the wrong material actually increases your radiation dose because you are being sprayed by the secondary particle shower.
So the metal wall essentially becomes a radiation multiplier. That is horrifying. How do you stop GCRs without generating that secondary shower?
Radiation shielding against GCRs is ultimately a game of bulk mass. You need a massive amount of dense material, preferably containing lighter elements, between the human tissue and the cosmic rays to absorb and slow down the particles safely.
Water is an excellent shield, right?
Water is excellent, but water is incredibly heavy and precious. The most abundant, readily available bulk mass on the moon is, once again, the regolith.
So that same 3-meter-thick igloo of sintered lunar dust that is protecting the habitat from the temperature swings is simultaneously acting as a massive radiation sponge.
Exactly. The sheer density and depth of the regolith overlay absorbs the primary cosmic rays and contains the secondary particle showers before they can penetrate the pressurized volume.
That solves both problems at once.
And interestingly, in certain regions of the moon, particularly near the poles where we suspect water ice is trapped in the permanently shadowed craters, the regolith may have a higher hydrogen content.
Which would make it even more effective at stopping high-energy neutrons.
Precisely.
It is a stunning convergence of solutions. You take the pulverized rock that fundamentally threatens to destroy your spacesuit joints and abrade your lungs, and you pack it around your fragile aluminum pressure vessel. And suddenly, that exact same abrasive dirt is the only thing keeping you from freezing to death, boiling alive, or being irradiated by solar flares. It becomes a solution embedded within the problem. I want to pause on that phrase for a moment, because I think it captures the essence of this entire technological leap. A solution embedded within the problem.
It's a great way to phrase it.
You don't have to import the answer from Earth. The answer is waiting for you inside the hazard itself, provided you have the engineering ingenuity to reorganize its geometry and chemistry.
It is a profound philosophical shift in how we approach engineering and survival in extreme environments.
How so?
For a long time, the dominant engineering mindset, particularly during the space race of the 20th century, was one of brute force opposition. We encounter a hostile environment, and our immediate instinct is to build an impenetrable fortress against it.
Right, keep nature out.
We try to dominate the environment, isolate ourselves from it completely, and overpower its harshness with sheer technological might, energy expenditure, and resources brought from home.
It's the mindset of a conqueror arriving in an armored tank. You view the environment as an enemy to be kept on the outside of the glass. But what you're describing with ISRU, using the regolith's nanophase iron for microwave sintering, using its sharp edges for mechanical locking, using its mass for thermal and radiation shielding, that is the mindset of an adapter.
That is the crucial distinction. When you realize that the solution to the extreme temperatures, the lethal radiation, and the destructive dust is to actively use the destructive dust to build the shields, you are no longer fighting the environment.
You are cooperating with it.
Yes. On a fundamental physical level,
Right.
You are acknowledging that the environment itself holds the energetic and material keys to surviving it. The problem contains the mechanics of the solution.
And this realization about lunar dust, it feels like it isn't just a clever engineering trick for one specific rocky body. It completely rewrites the rules of how humanity will expand into the universe. We are looking at a great shift in space architecture, from Apollo-style camping trips to actual sustainable settlement.
If we connect this to the bigger picture, it changes the entire long-term trajectory of human spaceflight. Traditional space missions, by necessity of early technology, treated extraterrestrial environments as barren, hostile terrains requiring constant resupply.
Everything had to be brought with them?
Right. Every single human spaceflight mission to date has essentially been a sortie. You go out into the hostile unknown, you carry your entire life support system and every gram of consumable material on your back, and you must rush home before your finite supplies run out. It is a model of profound, inescapable dependency.
The umbilical cord stretching all the way back to Earth. If the supply ship doesn't launch on time, the astronauts run out of air, water, or shelter.
Exactly. But the emerging ISRU paradigm treats these environments not as barren voids, but as resource-rich ecosystems waiting to be processed. Survival and eventual expansion no longer depend on how much mass you can launch from Cape Canaveral. They depend on your capacity for local adaptation and the chemical utilization of what is already at your destination.
So what does this ultimately mean for us? For you, the listener, thinking about the future of space exploration, what is the core takeaway? Because this isn't just about the moon, is it? The moon is serving as a laboratory. It's the proving ground.
The moon is the ultimate workshop for human expansion. It is only 3 days away, and it possesses one of the harshest, most unforgiving surface environments we know of.
If we can make it there.
If we can master local adaptation and self-sufficiency on the moon, if we can learn how to autonomously center our landing pads, print our habitat shields out of the very dust that tries to destroy our machinery, harness the local solar energy to power the magnetrons, and eventually extract oxygen directly from the silicate rocks, then we have forged the blueprint for going anywhere in the solar system.
Because if we can solve the puzzle of survival on the moon, we can apply those exact same principles of materials science and in situ utilization to the Martian regolith, which has its own unique toxic perchlorates and challenges.
We can apply it to the moons of Jupiter or to near-Earth asteroids.
Human expansion won't be defined by stubbornly trying to replicate the atmospheric and structural conditions of Earth everywhere we go. We won't be carrying little fragile imported aluminum bubbles across the galaxy. We will be learning to work with alien chemistry, adapting our architecture to the local mineralogy rather than fighting against it.
It marks the critical transition from being mere visitors in space, surviving on rations brought from home, to becoming true inhabitants of the solar system. And that profound transition requires a fundamental shift in perspective, one that begins right here, with how we choose to view a handful of jagged, statically charged, incredibly dangerous lunar dirt.
It is truly an incredible intellectual journey when you step back and look at the arc of this scientific development. We have gone from the Apollo era, where this fine, invasive, chemically reactive menace was the absolute bane of astronauts' existence, a microscopic hazard that threatened to derail the entire concept of long-term planetary surface operations,
to today, where those exact same hostile properties are being actively harnessed.
The sharp, unweathered edges are interlocking. The embedded nanophase iron is coupling with microwave energy to fuse the dust into radiation-shielding vaults and vitrified landing pads. We are literally laying the foundation of our first off-world cities using the very obstacle that stood in our way.
It forces us to reconsider how we approach massive systemic challenges entirely. And it leaves me with a lingering thought that I think is worth considering far beyond the realm of astrophysics, material science, and space exploration.
What's that?
If the moon's greatest, most frustrating obstacle, a pervasive hazard that seemed entirely irredeemable and fundamentally opposed to human presence, is actually the foundational raw material for our survival and expansion there, it makes you wonder what other seemingly insurmountable, universally dreaded problems right here on Earth are actually just profound solutions waiting for us to change our technological perspective.
That is a powerful and provocative thought to leave on. Maybe the very friction points we are fighting against in our own environments are the exact raw materials we need to build our way forward. We just need to figure out the right frequency to apply and learn how to lock the jagged edges together. Thank you for joining us on this conversation about lunar regolith, the tyranny of the rocket equation, and the brilliant future of in situ resource utilization. Keep questioning the nature of the obstacles in your path. Keep looking for the elegant solutions hidden inside the most difficult problems. And as always, keep looking up.